Hello everyone. Today I'll be presenting on graph data structures, one of the most powerful and flexible tools in computer science. A graph allows us to represent relationships among entities. These entities are called vertices or nodes, and the connections between them are called edges. Graphs can be used everywhere, from analyzing social networks to finding routes on maps and also to modeling communication systems. So let's talk about the definition of a graph. So a graph consists of nodes which hold data and edges which show how those nodes are related. Depending on a particular problem, these graphs can be finite or infinite. And essentially, it is a structure that lets us model anything where relationships matter, whether it's people, cities, or even web pages. So let's start talking about the types of graphs. So graphs come in several types, as shown in the presentation: directed graphs, undirected graphs, weighted graphs, and unweighted graphs. So what is a directed graph? A directed graph has edges with direction. For example, when one web page links to another, but not the other way around. It's like a one-way relationship or a one-way street or road. So what is an undirected graph? It is the opposite of a directed graph. So it means the edges can go both ways, like friendships. Like if you're a friend with another person, so that another person is also a friend of yours, like the friend system on a social network. So let's talk about weighted graphs. Weighted graphs assign a cost or distance to each edge. It is what navigation apps use to find the shortest route. So apps like Google Maps or delivery apps use this particular system of graphs and also algorithms to implement the shortest route. And also, let's move on to unweighted graphs. So unweighted graphs do not have weights. They are used in simpler cases where all relationships are equal and that no value is required for the edges. Now let's talk about the methods of representation. So graphs can be represented in multiple ways as shown. First of all, it is going to be a matrix of adjacency or an adjacency matrix. It uses two-dimensional arrays. It is simple, but it can usually waste space if the graph is sparse. Let's move on to list of adjacency. The adjacency list is more efficient for sparse graphs as each vertex only stores its direct connections. So it doesn't require lots of space like the matrix of adjacency. So it's better to know the pros and cons so you know when to use these methods. And lastly, it is the edge list. So the edge list focuses on the edges themselves. It is useful when we need to process connections directly. And there is an algorithm called Kruskal's algorithm that implements or that uses this particular representation. Now let's talk about common algorithms regarding graphs. First, we have depth first search is DFS. It explores as far as possible along each branch before backtracking. It is similar to diving deep into a maze. You can also use depth first search for other data structures like binary trees and other types of trees. Next, we have breadth first search or BFS. It explores level by level, making it ideal for like finding the shortest path in unweighted graphs. Now let's talk about Dijkstra's algorithm. And this algorithm is very popular among graph data structure, and this algorithm finds the shortest path in weighted graphs. The A-star algorithm enhances Dijkstra's algorithm to make the search faster and smarter. So it's very advanced. Maybe in the future I will make a video on it. So make sure you subscribe and click on the notification bell so you get notified when a new video comes out. So let's start talking about adjacency matrix. So what is an adjacency matrix? It is a grid that shows which vertices are connected. It is a two-dimensional array. I will show you the visualization of the array in the next slide. Adjacency matrix has rows and columns that represent vertices, and the cells contain either 0 or 1 to indicate whether an edge exists. So just like I said here, 0 means no. It means there is no edge between the row and column, which are vertices. And if the cell contains 1, it means there is an edge between these two vertices. While it allows a quick O of 1 access to edge information, it can be memory heavy for very large graphs, and it is really heavy. As for example, if you have like 4 vertices, and if you want to store it in an adjacency matrix, you will have to have like 16 spaces for it. Imagine using the exact same representation for a, a graph that is like, say, 1,000 vertices or even 10,000 vertices. The number would go exponentially. So let's start implementing the graph. So for implementation, we need to define several interfaces and some helper classes. So first, let's go with the edge interface, and it will define the operations for the edge behavior. Then we have graph interface, which outlines the methods for adding, removing, traversing the graph, etc. Next, we have the position class. The position class will store information about where the elements are placed, like the index, and we will also have the value of the element. Next, we have vertex interface. The vertex interface defines how each node stores data and interacts with others. So it basically has to do with the vertexes. Now let's talk about vertex and edge interfaces. So for the vertex interface, we have uh, 3 methods, and it describes the structure of a node, and it's also generic, so you can put in any type of data, names, numbers, or objects. It doesn't matter because we're using generic. It is also applied to edge as well. Similarly to vertex, we're also using generics here, so the edge value can be anything, any type of data. It can be names, it can be numbers, it can be objects. Now let's talk about the position class. The position class acts like a locator. It stores both the element and its position in the data structure. And this class isn't limited to graphs. It is also used in lists and trees to make navigation easier, as you will see in future videos. Here we have the graph interface. The graph interface defines the entire structure, combining vertices, edges, and all core operations. It is also generic, so you can use this for other representations as well. In fact, you can use all these interfaces and classes including the position class for adjacency list graph as well. So here, as you can see, here is the visual representation, or I mean visualization of the adjacency matrix. So on the left side, you can see the matrix. It's a grid. It is a two-dimensional array, and it's better to look at it this way if you visualize it. And on the right side, you can see the graph representation. Each one in the matrix corresponds to an edge between two vertices. Let's say for the vertex 0, it has an edge towards vertex 1. As you can see, 0 of 1 is 1. It means there is an edge between vertex 0 and vertex 1. The same goes for other connections, like for vertex 1, there is a connection towards vertex 2. Also from vertex 1 to vertex 3, all of them have 1 in it in the matrix. That means there is an edge between them.